I'm delighted to be able to start the workshop by introducing this year's invited speaker, David McQueen. And Professor McQueen has been involved from the very early days of ML and has published seminal work on the design and implementation and semantics of the language. He's perhaps best known in this community as a designer of the standard ML module system, as an author of the SML definition. And I had the pleasure a few months ago of attending a short talk by Professor McQueen on the early history of ML, and I knew that you'd all enjoy hearing about that, and so have invited him to give a more extensive account of those early days and the various influences on the design of the language. So I'm very much looking forward to hearing the talk, and hope that you'll now join me in welcoming Professor David McQueen.
Thank you. Good morning. Oops, oh dear. This is a bad omen. Let's see where we are. My papers. Sorry. Okay. Now I have to figure out where I put this. Here it is. Okay, let's try it again. Oops. Okay, so far so good. So I thought I would try to set the stage by going back a little bit further in history to the 50s and 60s and even beyond, and talking about some of the personalities that really established the British programming language research community and culture. And so you can start with Max Newman. Everybody know who Max Newman was? So he was a topologist. Oh, yeah, right. I have to stand here. He was a topologist at Cambridge who was a mentor of Turing's. He gave a course on the Gödel incompleteness proof that Turing attended, and that was where he became interested in the Entscheidungsproblem. And he then sent Turing off to study with Church at Princeton, where he got his PhD. And then later on, he became the head of the computing machinery laboratory at Manchester and hired Turing there. So Alan Turing we all know about. So Turing had a friend, Christopher Strachey, who was probably the central innovator and leader of early programming language research in Britain. And I'll talk about him later. Then Peter Landon, Rod Worstell, and Robin Milner could fit on here as well. So who is Mervyn Pragnall? Mervyn Pragnall is the catalyst. He brought people together. So here's a story from Peter Landon. You can actually watch him tell this story on a talk he gave that's available on Vimeo. So he went to a cafe. He had finished his Cambridge degree and hadn't figured out what to do with himself, and he was living back home in Sheffield. And he was spending a lot of time at the Sheffield Reference Library, and he was in a cafe next to the library when suddenly somebody accosts him and says, "I say, didn't I see you reading Principia Mathematica in the reference library this morning?" Anyway, this person turned out to be Mervyn Pragnell, who then invited him to join his informal reading group. So this was in Sheffield, but several years later in London, Rod Worstell was working as a programmer, I believe, at Ferranti. Most of these people at some point worked as programmers at Ferranti or Elliott Computers. And he was looking for a logic book at Foyles, which is a big bookstore in London. And he asked a person standing nearby about whether they had the book, and that person says, "I'm not a shop assistant," and walked away. And then he came back to invite Rod to join his seminar. Anyway, so this seminar was held at Birkbeck College, which is part of the University of London, after hours, and in a kind of underground fashion. Pragnell knew a lab technician who had a key to the building, and so he could get in at night. And so he and his seminar or study group would go there at nights and meet and talk about logic and category theory and computing and so on. And this is where Landon probably first met Strachey. This is where Rod Worstell met Landon and Strachey. Robin Milner admits to having attended it once or twice. So all these people came together in this amateur, informal, underground seminar to study logic and computing. This is, to me, a remarkable thing that characterizes the kind of informal and kind of amateur view of life, which was a rather attractive, in contrast to the United States, a rather attractive feature of British academia. Of course, these were not academics. These were working programmers. And so to look at Strachey in particular, as I mentioned, he was a friend of Turing, first at Cambridge socially, and then at Manchester. In the early 50s, he wrote the first checker playing program. He was working at the National Physical Laboratory in London. This is probably the first game-playing program, in 1951. And he also, after he started going up to Manchester to use the Manchester Mark I, because it had a lot more memory than the Pilot Ace machine that Turing had designed and they had built at NPL. Anyway, he wrote a program to play songs like Ba Ba Black Sheep on a kind of hooter, whatever that is, that attached to the Manchester Mark I. In terms of programming languages, one of the designs he was involved in and led was called Combined Programming Language, or CPL. Originally, it was called Cambridge Programming Language, but then the project added somebody at London University, so they called it the Combined Programming Language. And of course, a lot of people nickname it Christopher's Programming Language. So one of the things that characterized that language was that functions, it had functions as first-class citizens, which is, of course, important to us. It introduced the notion of L values, expressions that evaluate to a location to be stored into. And of course, after the CPL was never really successfully implemented. There were prototype implementations both at London and at Cambridge, but the language was very ambitious and complex for the time. So these compilers never really got off the ground and had users. However, Martin Richards at Cambridge wrote his thesis on a CPL compiler, and then afterwards decided it might be better to try to strip the language down a bit. So he invented basic CPL, BCPL. Now and then he implemented it. And BCPL actually became a fairly popular systems implementation language in the late 60s. It was used in the early 70s. It was used, for instance, at Xerox PARC to implement some of their systems in the early days. And at Bell Labs, Ken Thompson got a copy and started using it and decided he could improve it, so he developed a language called B, and then Dennis Ritchie came along and improved that to C. And of course, the rest is history. Another thing he did is he coined the term currying. And he wrote a very important paper in the mid-60s. It was presented at the Copenhagen conference in 1967 called Fundamental Concepts of Programming Languages, which everybody should read at least once. And one of the things he talked about or introduced in that paper was the notion of parametric polymorphism. He talked about several varieties of polymorphism, one of which was characterized as parametric. Of course, he's also well known for the Scott-Strachey denotational semantics method. Now, the descriptive aspect of the notation and the descriptive techniques of denotational semantics were already something that Strachey had been working on, and Dana Scott came to Oxford in '69 and provided a mathematical foundation in domain theory, having just discovered the D-infinity model of the lambda calculus. Chris Wadsworth was a student of Strachey and wrote a thesis, an important thesis that involved graph reduction for the lambda calculus, but they also jointly wrote a paper on continuations, which is one of the first formal studies of continuations. He came up with the notion of time sharing in 1958 in a somewhat limited way, but and he employed Peter Landon from about 1950. He had worked at the National Physical Laboratory and then the National Research and Development Corporation in London, and then in 1959 he became an independent computer consultant working for various companies like Ferrante and NRDC. And he employed Peter Landon as his assistant for 4 years. So here's what Chris Wadsworth says about Strachey. He had an acute sense of when something was right, generally when it was simple enough and elegant enough that it could be seen intuitively to be right. And he abhorred over-elaboration or contrived methods that sort of worked, i.e. hacks or kludges. A favorite motto of his was, "You can push a pea up a mountain with your nose if you really want to, but that does not mean that is a good way of getting it there." For me, this was a kind of Strachey test. And Rod Worstell says of Strachey, his elegance of manner was accompanied by an elegance of thought and language, which was a continual inspiration. So Peter Landon, I think I can describe Peter Landon basically by showing this burst of papers in the mid-60s that really changed computer science, or programming language, forever, the programming language field forever. First was the mechanical evaluation of expressions, in which he introduced the SECD machine. This was not necessarily the first abstract machine. He credits people at Munich in the Algol community for having talked about abstract machines that inspired him. Then he did a translational semantics of Algol 60 by translating the language into the lambda calculus. And there are a number of interesting technical innovations in the machinery that he used. For instance, he introduced the notion of streams as a technical device for dealing with I/O. His paper on jumps and labels, or what's called Landon's J operator, was a kind of precursor to first-class continuations, and which was adopted, for instance, in the Edinboro POP2 language. And then, of course, a paper that every one of us should have read by now is the next 700 programming languages, which essentially describe the ISWIM language. ISWIM is an acronym for If You See What I Mean. I don't know where the Y went, but of course that became the foundation of the design of ML. Then he wrote in 1969 a paper on programs and their proofs, an algebraic approach with Rod Worstell. And this foreshadows the notion of algebraic data types. There was a kind of proto-algebraic data type in Landon's papers, like the ISWIM paper, but it was an extra-linguistic notation or style for describing data structures. It wasn't actually part of the language. And then I should mention that there was an early implementation of ISWIM called PAL, which was the short acronym for Pedagogical Algorithmic Language, at MIT by Arthur Evans. Actually, Christopher Strachey, this PAL project had been going on for most of the 60s, because in the early 60s, Christopher Strachey went to MIT a couple times and worked with Evans on this PAL project. But it wasn't until Landon went to MIT and spent a year in 1967 that the PAL language sort of gelled and became essentially a version of ISWIM. I, of course, should mention Robin Milner. Probably some of you saw Mike Gordon's 2010 ICFP invited talk about Robin, which was great, so I'll just go through the usual details. Again, like Strachey and Landon, Robin didn't start as an academic. He was a school teacher, secondary school teacher, programmer at Ferranti, and then he decided that was boring and he wanted to get into academics. He was interested in how things worked. So he went to the City University of London, then had a research assistantship at Swansea, then he went to Stanford, worked with Richard Weirach on the Stanford LCF system, came to Edinboro in early 1973, and of course, we know what he did there because it's all described in his Turing Award thing. Anyway, but this is an interesting quote. The idea of a machine proving theorems in logic and the idea of using logic to understand what a machine was doing, this double relationship began to inspire me because it was clearly not very simple. This is about the time when he was at Swansea. So these are the principles that these people lived by. First, they realized the importance of foundations and semantics in the study of computation and programming. They wanted to reason about what was going on and understand it in a rigorous way. So they were seeking clarity, rigor, and elegance through the use of mathematics, mathematical ideas, particularly from logic and algebra. Of course, later on from category theory, other areas, homotopy theory these days. And of course, these ideas pervaded the Edinboro community. So now, finally, we get to Edinboro in the late 1970s. This is basically when I came on the scene. I arrived at Edinboro in May 1975. So Robin had been working on the LCF theorem prover, first with Lockwood Morris and Malcolm Newey, then with Chris Wadsworth and Mike Gordon, who arrived about the same time as I did. And in about 1978-79, they had the system working, and they published the LCF book and publicized ML in Popple and the LCF system. And Robin wrote his paper on type inference, which was published in '78. Also, Luca Cardelli arrived in Edinboro as a grad student in the fall of 1978, and he had a major impact. Rod Worstell and I were working on the HOPE programming language, which is a purely functional language whose most important contribution was the algebraic data types. That was the first language with algebraic data types and pattern matching and causal function definitions, etc. Although Rod Worstell, the year before, had done a little toy language called NPL, which sort of sketched algebraic data types, but in a kind of a different style, where the constructors could be added to a type at will. So also, there have been two sub-communities at Edinboro. The Worstell community was in the School of Artificial Intelligence at Hope Park Square, as was Rod Worstell and Gordon Plotkin and their students and postdocs. And then Robin Milner was in the computer science building, the computer science department, which was in King's Buildings, 3 miles to the south. And so that 3 miles was a major barrier between these two groups. We didn't casually walk back and forth or take the bus back and forth. So another mechanism was found to connect the communities, which was the Bob Boyer Memorial Society. Bob Boyer had been a PhD student in the AI department working on the Boyer-Moore theorem prover. Well, no, he had been a postdoc. Jay Moore was the PhD student. And when Bob Boyer left to go to SRI, his community building efforts were missed, and so they started having evening seminars every other week at people's homes, mostly Rod's home or Robin's home, because the rest of us were living in hovels. Anyway, so we'd have an evening seminar, usually with refreshments, in somebody's living room. And this kept the two communities in close touch until they were physically unified at King's Building in the late '79. And of course, that basically formed the nucleus, which later became the Laboratory for Foundations of Computer Science at Edinboro, which was formally founded in 1986. The other person besides Rod, Gordon Plotkin, Robin Milner, was Matthew Hennessy. He was the sort of fourth founder. So Edinboro was extremely well connected at this time. It was fantastic. I was extremely lucky that I decided to go to Edinboro at that time, because it seemed like the center of the universe in terms of programming languages. So the three key personalities were Worstell, Plotkin, and Milner, but then there were a lot of other people. Below are Lockwood Morris and Malcolm Newey, who were the first generation LCF implementers, and then Mike Gordon and Chris Wadsworth, and then a bit later, Mess Tofta. Bob Harper did a postdoc there and was there for quite a long time. John Reynolds, Bob Constable also spent a lot of time, were regular visitors. Joseph Gogin worked with Rod Worstell on algebraic specifications. There were a bunch of postdocs and grad students, Kevin Mitchell, Alan Mycroft, John Scott, and of course Larry Paulson from Cambridge was never at Edinboro, but he was strongly connected. And then there was this other community at INRIA. Gilles Kahn, who spent the year 75, 76 at Edinboro. Gerard Douet, Guy Cousineau, Gerard Berry, Jean-Jacques Lévy, and others. Basically, there was a continuous traffic back and forth between Edinboro and INRIA, this particular group in, I think it was Bâtiment 8 at that time. And there was actually a formal funding grant that provided travel expenses specifically for traveling back and forth between INRIA and Edinboro. Did I leave anybody out there? Don Sinella should mean. Oh, Von Pratt. So Von Pratt, his role, he spent the summer of 1975 at Edinboro, and through that visit and also through Malcolm Newey, who he knew from Australia, he introduced the von Pratt precedence parser technology, which is all we knew about parsing at the time. Quickly survey what was involved in the LCF version of ML. So I'll call it LCF ML. It was, of course, embedded in as a part of the LCF system and used it as its meta language. It supported the object language, which was called PP Lambda, which encoded Scott's LCF logic with terms, theorems, and formulas. And the key thing was that theorems were an abstract type whose where the constructions of values could only be performed by inference rules. So if you created a value of type theorem, you knew that it had to follow from the inference rules of the logic. And it had a quotation, anti-quotation mechanism for embedding object language syntax into programs. And it, of course, used the higher order feature. It had proof tactics, which were functional objects, and higher order tacticals for combining those. So that's why they needed a functional language. They also needed a strongly typed language to make sure that there wasn't a backdoor for creating theorems. So in terms of the language design, as I said, it was based on ISWIM. Milner's type inference, let polymorphism, was a really big idea, and it made the language much more flexible, etc. It had abstract types, which were probably influenced by the CLU cluster idea, where you had isomorphisms, abs and rep, back and forth between the representation and the abstract type. It had simple binary products and sums. It had mutable variables that were introduced with a letref declaration, and had a rather obscure typing rule to deal with the interaction between updates and polymorphism. It had var structs, or patterns, that were constructed out of variables and tupling and lists, so it's a kind of limited form of patterns. It had a fancy loop conditional that allowed looping, so you could say, instead of if then blah, you could say if loop blah, which meant that if you took that branch, you executed the expression and then looped back to the thing. So that was clever. And there was an even more fancy failure trapping mechanism, which was based on passing strings, or what we call tokens in ML. But there were simple traps. There were traps that were conditional on the string, and then there were or lists of strings, and then there were looping traps that would trap and then redo the expression. So it was a fairly hairy failure mechanism. So the implementation was done in Lisp, initially Stanford Lisp, later in Rutgers Lisp, and then there were other ports to other Lisps at Cambridge and Gothenburg. And INRIA. The compiler translated the ML code into Lisp code and then interpreted the Lisp code, so it was pretty slow. And the parser that was used throughout this, and then also in Hope, was this von Pratt's precedence parser, which had a peculiar thing that you attach parsing routines to symbols. And so by its nature, it was a little bit awkward or unnatural to have more than one parsing semantics for a given symbol. So if you used up comma for pairing, you needed something else for, statement separators, or so you need use, or for say list separator. So you use semicolon for list separator. And then you've used up semicolons, so you need something else for statement separators. So you use double semicolon. And so this is a consequence of a neat hack for parsing that had its limitations. So also, Luca was a PhD student with Gordon Plotkin working on a hardware design language for his thesis, but he thought it'd be fun on the side to write a compiler, so in 1980 he starts work on his own ML compiler. He changed the language in interesting ways, so he had a Cardelli dialect, and he implemented it in Pascal on the VAX VMS system in the computer science department. Within about a year, he had a working compiler, and by the end of 1981, it had already been distributed to a number of places. And it was all written in Pascal, no assembly language, no C. We didn't know C in those days. Unix had just kind of barely made it to Edinboro. But he even wrote the garbage collector in Pascal, just like writing the compiler, the garbage collector in the Orbit compiler in Scheme. Okay, so there was sparse documentation, but the interesting things is it added labeled records. Structural, these were record types and variant types that didn't need declarations, they just existed. They were just intrinsic constructs in the type system. And this was partly inspired by Plotkin's lectures on domain theory. He had a set of declaration combinators, which I'll talk about very briefly. He introduced, instead of letref, he had the ref construct. This is something that Mike Gordon had set a little research program for Louis Demas to investigate refs as a type operator instead of a kind of ad hoc letref construct. He did so and wrote one chapter of his thesis dealt with this. And Luca borrowed some of those ideas and implemented ref as a type constructor in his compiler. He had stream I/O, and he had a basic module system that had an interesting fact. Interesting fact was that modules could be stored by being serialized into a file and then reloaded, etc. These are the declaration combinators. It was a kind of calculus of declarations, but it was a little bit too much. So basically, later on, it was trimmed down to just the enc, which is enclosing, which means basically sequential, normal sequential composition of two declarations. And then ints, or inside, which was applying a declaration, having a declaration whose scope was another declaration, but whose bindings were not exported. So that became the local declaration construct. And then you could add the rec keyword, and with was a special thing having to do with the combinator for creating abstract types. As I said, this ran under VMS in Pascal. Oh, the functional abstract machine. So it compiled to an abstract machine called the FAM, or functional abstract machine, which had a big impact. That was published in the 1984 Lisp and Functional Programming Conference. Generated native machine code. So what did it accomplish? Well, it demonstrated that ML was a viable standalone programming language. It also created a worry that now there was more than one dialect of ML. And so this led to some discussion, eventually a discussion between Bernard Suffren and Robin Milner about something should be done. And that led to the standard ML proposal. It was one of the inputs to the standard ML design, and during the early years of the standard ML design, Luca modified it by adding standard ML features as they were discussed. So the real standard ML design started in April 1983 when a bunch of people happened to be in Edinboro. It was somewhat fortuitous. Robin had actually, at that point, written a draft language proposal, the first draft, the tentative draft. And so I happened to be spending a month in Edinboro. Luca Cardelli was there. Mike Gordon and Larry Paulson were able to come up from Cambridge on short notice, and there were about 9 Edinboro people. We had a meeting to discuss in Robin's living room, a meeting to discuss his proposal. And out of that came a lot of comments and discussion and correspondence and so on. Here's who was at that first meeting. About 9 of the physical participants were people who were already at Edinboro, and others were visiting. And the proposal had been sent to a number of people like Gerard Huet and Peter Mosses and David Schmidt. Although David Schmidt, I'm not absolutely sure where David Schmidt was at this point. He may even have been there. Unfortunately, nobody was taking minutes at this particular meeting, which was too bad. So it's hard to construct exactly who was there and exactly what happened. But here's the first page of the proposal. This is about 25 pages of handwritten script. And here's a sample piece of code from the thing. So it looks fairly like current standard ML. You can see the resemblance. But of course, there are minor differences. There's the var instead of val, and there's rec data instead of just data type, and so on. He had already chosen the of keyword for data types. Another thing, and he's using backward arrows instead of equality in many places. He also had already labeled, as I show you, he had already labeled the language standard ML, expressing a hope that this would stop the forking of the language design and everybody would concentrate on a single design. That was a mistake. Well, it was a mistake for that tentative name to stick as it did. There should have been a serious discussion about what the language should have been named, but there really kind of never was, or at least serious enough to change things. So there was the data types from Hope were brought in pretty much as they were, with the minor syntactic changes like the of keyword. The records and variants of Luca's VaxML didn't make it. It already introduces clausal function expressions with multiple clauses or cases. References and equality were treated in a very restrictive way. The reference values were expected to be monotonic, and equality was only on monotonic types. Local was introduced as a replacement for Cardelli's INS declaration operators, and then the fancy escape mechanism of LCFML was discarded in favor of a fairly standard trap mechanism, but with a clausal handler with var structs v1 or patterns v1 through vn, discriminating on the exception. But the exceptions were still only carrying strings. So the actual v1 through vn would just be string values as the patterns. Now then there was a whole sequence of further proposals with lots of discussion and correspondence. This was not easy because this was before the ARPANET and certainly before the World Wide Web. And so even email between Edinboro and say Bell Labs, where Luca and I were, was problematic. And a lot of the correspondence was actual physical correspondence, handwritten notes and letters sent back and forth between people. In 1984, in June of 1984, there was a second meeting in Edinboro. This was attended by a relatively small group, but the core people were there, except for Luca. And out of that, there was actually a report. Robin and I wrote up a record of the meeting. Then there were further refinements. Basically, all these are sort of incremental steps toward the final standard ML language, so I'm not going to detail all of the changes along the way. Although all of this will be on the standard ML family history website. And there, in 1985, there was actually the second standard ML meeting, which was actually called the ML workshop. So that was the very first ML workshop, 1985 in Edinboro. And there was a large group of people who attended that, and there were about 26 documents in the meeting record, various proposals and commentaries and so on. And Bob Harper wrote up a report on the meeting. And then finally in 85, there was the standard ML core language revised, which was sort of the final draft before work on the formal definition began with Robin and Mess Tofte and Bob Harper and myself kibitzing. There were some side threads of proposals. There are several proposals on Stream.io, and there were several drafts of my modules proposal, so on. And then starting at 86, Robin and Mess in particular got down to writing the formal semantics, which became the book. And there were roughly annual editions of that published as Edinboro Tech Reports. And then finally, in 1990, it was published by MIT Press. One core language innovation took place rather late in the process. After the definition had started, there was the proposal to treat exception values as an extensible data types, where you would declare at will exception constructors, and then you could pattern match over the exception constructors in handlers. So Andrew Appel and I wrote a proposal for that, and then that was updated and sort of integrated into the definition with Robin and Mess Tofte. There are three early implementations. I mentioned that Cardelli ML kind of evolved toward standard ML a ways. We called it substandard ML. Edinboro ML was another implementation where Alan Mycroft and Kevin Mitchell took Cardelli's compiler and rewrote it in itself so that it could bootstrap itself. And that was called Edinboro ML, and it was originally basically the same dialect as Cardelli, as VaxML. And then they evolved that during the ML design process into something that was approximately standard ML. And we actually used that, Andrew Appel and I used that to begin developing standard ML in New Jersey later on. And Dave Matthews had a compiler for his own language, Poly, which was a kind of inspired by the Russell language, has typed as first-class values. And he wrote a standard ML front end for that, and so quickly was able to produce a standard ML compiler, and that's still going, as we'll see later today. There's a long catalog. If you look at the website that I'm going to tell you about, there's a catalog of implementations, but these are sort of the major ones in the sort of intermediate period. So what are the big ideas? Let polymorphism, type inference, and principal types. That's clearly a huge idea, hugely influential. Now, it's often called Hindley-Milner, but it should be called Curry-Hindley-Milner because Curry and Hindley both did a type inference for the lambda calculus paper independently in 1969. But it also should be called Newman, Curry, Hindley, Milner, because it turns out that Max Newman, who I told you about at the beginning, wrote a paper in 1943. He was actually at Bletchley Park at that particular time. He may have written the paper earlier. But it essentially gave a way of doing typability checking for for Church's simple theory of types. But in fact, if you look at the algorithm, it's easy to take it a little bit further and do type inference. So it goes back to 1943 at least. Who knows where else it was invented. Algebraic data types from Hope was a major idea. The module system with signatures, functors or module functions, and sharing specifications, which is regarded as a kind of mystery, but it's kind of automatic if you do the exercise of trying to just abstract over modules. You find you need sharing specifications or the equivalent. It also had in its original form a somewhat controversial feature called generative structures, or structures that had their own unique static identity, which could be statically checked. So you could statically, at compile time, check whether two structures were identical. And that was a bit stronger than saying the types within the structures were identical. But it caused a bit of a mess in the semantics, so it was not entirely popular. But it had its rationale. Exceptions as an extensile data type, I mentioned, and it introduced polymorphism for ref variables via this notion of imperative type variables, which led to a big mess. Many papers written about how to improve this proposal or finally to eliminate it, and Andrew Wright finally made the case for eliminating it. So just yeah, I'm running low on time. So the algebraic data types, as I meant, came through Hope, but they really started in ISWIM and were semi-formalized in this Landon and Worstell paper, and in Worstell's toy language, NPL, and then finally fully formed in Hope, and then transferred to standard ML. So this is the informal data type-like description language that Landon used in his papers. And it's rather similar to a data type modulo, things like there's no constructor for the identifier case of expression. Mistakes in the design process. Freezing the formal definition in the form of a book was a mistake. This had to do somewhat had to do with Robin's attitude toward the project. He was a busy guy. This was a kind of secondary project where his primary project, his foreground project, was CCS and the pi calculus. That was taking up most of his time. So he wanted to have a kind of sunset. He wanted to have a point where he could stop thinking about this. And handing over the manuscript to MIT Press was his endpoint. So for his purposes, he didn't expect to implement, maintain, or even use the language. But if the language is going to be implemented and maintained and used, the definition is something that needs to be maintained as well. And at that time, the World Wide Web didn't exist. So putting it online was technically not really an option, but we've corrected that at a website called smlfamily.org, where the definitions are now online, and one of them is even evolving. The other major mistake was that the book, the SML90 book, had a small, like 2 or 3 page appendix describing what was called the initial basis, which was the sort of built-in library of types and operations and so on. And it was totally inadequate. There were about 43 items in that initial basis. So of course every implementation had to vastly extend that, and every implementation did so, but in incompatible ways. And so it took a long time to try to get that back together, and finally the John Reppy and Emden Gansner developed the standard ML basis library, but that didn't get published until the 2000s. So that was a drag. Okay, very briefly, in the 1990s, there was further activity. The main activity was standard ML 97, which was a revised definition, and then ML 2000. So in 97, at the Newton Institute, there was a program on semantics of computation for 6 months, and Milner, Harper, Tofta, and myself were there in Cambridge, so we decided to start working on a revised definition. So these are the main things. Type abbreviations and signatures were introduced. I had already implemented those in early 1993 in Standard ML New Jersey, and then Harper and Leroy published papers in Popple in 94 about essentially the same idea. And then opaque signature matching, another thing that I had implemented earlier in the Standard ML of New Jersey. Weakening the notion of structure identity and structure sharing so that it only represents implied type sharing, which cut out about 3 pages out of the semantics. Value polymorphism to eliminate the imperative variables having to do with references, huge win. And replication of data types, which is a small technical thing. One thing that Bob Harper and I really wanted to do was also eliminate equality type variables, but we didn't manage to convince Robin and Mess. I would have liked to have had higher order functors, which I implemented in Standard ML of New Jersey in 93 as well, but that was too far too. Then in 1993, Bob Harper and I were at Popple, I think in Albuquerque, and we decided we should start talking about a completely new language, which we called ML 2000. And we had a bunch of meetings with a bunch of really good people, but we just couldn't arrive at a consensus. And the big contentious issue was whether ML should become an object-oriented language as well as a functional language, whether it should be a hybrid object-oriented and functional language. And Bob Harper and I were strongly against, and other people were strongly for. Of course, OCaml did its own object extension, and Reppy and Fisher did the Moby language, which was a kind of new principle design to combine ML with objects. So I wanted to advertise this website we've set up, SML Family. Bob Harper and I set this up earlier this year, and it's a home for the online editions of the definitions of standard ML, and as well as a type theoretic definition from CMU, machine checked, and also a successor ML definition, which is actually being modified in a quiet way. and John Reppy is busy with revisions to the standard basis, revisions and extensions to the standard basis. So final thought, it's a lot of work going through these hundreds of documents and trying to figure out what's significant and so on. My ambition is to put a lot of this material, the raw material, those reports, but also commentary and so on, into this history website at smlfamily.org. It's difficult because you're reconstructing what happened 30 years ago, and memories have faded. Some people have died. Some critical people have died. And but I think it's worth it's fun in a way, and it's worth trying to understand in more detail the history of the ideas, where they came from, what the alternatives were, what the arguments were, etc. And with that, I'm finished. Thank you. Any questions? Jeremy?
On the subject of avoiding remaking old mistakes, sounds like the ML, the small basis in standard ML, reducing the mistakes of the algorithm design in the 60s, and also something from language specifications that didn't specify that library.
Indeed. Exactly. Algol 60 was a good precedent for that mistake. Yep.
I've been wondering for some time how much of initial algebra semantics was sort of designed to be baked into algebraic data types from the start. And I know that, Dogan, you mentioned, had been working on those ideas in roughly 74, and I saw you co-authored papers with Worstell
Yeah.
at nearly exactly the same time, but none of the papers made the connection.
Yeah, Gauguin was not really involved in the data type story. The data type story had already, basically developed quite a ways with Worstell's work with Landon and that history, the sort of ISWIM linguistic ideas. What did have a huge influence was Worstell and Gauguin's work on the clear specification language, which is a modular specification language based on algebraic techniques, and had in particular parametric specification modules. And that was one of my first starting points for designing the module system. The second starting point, or the other huge influence, was the Martin-Liff type theory, which led me to write the 1986 paper on modular structure and dependent types, which was not today's dependent types. This is types depending on each other. Yep.
On the second to last slide, you mentioned the successor now. Could you talk maybe a little bit about what's been going into that and what is there to do?
Well, so far, there's a backlog of criticisms and essentially semantic bug reports that have accumulated. There are several tech reports where people said, here's the mistakes in the standard ML definition. So initially, there's some effort to go back and through those and correct some of those mistakes. And this is being treated as a kind of modest incremental process as opposed to getting a committee together and having a language design. Basically, at the moment, most active people are the Milton people, John Reppy, Andreas Rosberg. And I'm going to be getting involved more heavily this fall. Yeah. Oh, yeah. Why don't you answer this? You're
Little bit of history there, that there were a few years ago that the national language before the definition had been liberated. There was actually a wiki that you talked about there set up that collected together a large number of ideas for how to evolve the language. Andreas Rosberg actually implemented a lot of these in Hamlet. The word Hamlet called Hamlet House, I think, is still available on webpage. And he also put together, as part of the manual for that thing, a collection of gifts that documentation on editors on, talk up this line, replace it with this, and that sort of thing. Change this rule in this way, or whatever. So I've actually taken them for promotion for the core language features that are a little bit more controversial. I've actually taken them and integrated them into versions of the definition. So there's sort of a document now that hopefully is a living document that describes the semantics of a modified version of that now, most of the changes have to do with record types and pattern. Other proposals on that, like
Yeah. Yeah, applicative record update and record concatenation are two well-known things that people have been talking about actually since 1983. There are actually notes in the early discussions about record update. Yeah.
So you mentioned some mistakes, and you've also mentioned a couple of times that you didn't have a large pieces like that.
Mhm.
And so looking at this, this seems like a very long process in comparison to what we do on today.
Exactly.
So can you say, were there any, sorry for the imagine here, but were there good things that came out of that? I mean, did it slowing you down?
I imagine one can speculate that having to write things out on pieces of paper and send them through the mail gave you one a little bit more time for thought and contemplation and so on, and then waiting for the reply to come back in a couple weeks. And